and start. Looks good. Let's see. Need to not go past this line without moving the camera. Okay. My textbook's over here. Okay, last week we ended briefly talking about complex numbers. So we introduced the definition of I and briefly talked about the complex numbers. So let's recap with a little bit of that conversation. So you remember our definition for I? What's I? It's the square root of negative 1, right? And so what's I squared?
Negative 1.
Negative 1. If I is equal to the square root of negative 1, then I squared is negative 1. Make sense?
Mm-hmm.
So then what's I cubed?
Negative I.
Negative I. How'd you do that?
Saw it.
So I cubed is equal to I squared times I. But what's I squared?
Negative 1.
Negative 1. So it's equal to negative 1 times I, which is exactly what we mean by negative I. All right, what's I to the 4?
1.
1?
So would I cubed be 1?
I cubed
Would be 1 squared.
is negative I.
Yeah, but would that go to 1 squared?
What's 1 squared?
1. So would it go to 1? If it's negative of a negative of I, that's positive I.
Oh, you're saying if I multiply this by I?
Negative I. I is already negative.
Negative I is
negative.
not the same thing as 1. No.
Negative I is the same thing as negative 1 squared, or root.
Negative root negative 1.
I is the same thing as negative 1, the root of negative 1.
I is the same thing as the root of negative 1. Yes.
And then times that by negative 1.
Times that by negative 1. So negative 1 times I is equal to the square root of negative 1 times 1, or times negative 1.
Which is 1.
Which is 1? How on earth are you doing that?
Never mind, okay, keep going.
Okay, because the square root of A times A is not equal to negative A.
Yeah.
Alright. Anyways, so I to the 4 we talked about. I to the, oops, here's our definition. I by definition is the square root of negative 1. I to the 4 then is the same thing as I squared squared, but what's I squared?
Negative 1.
Negative 1. What's negative 1 squared?
Positive.
Positive 1. Okay. So now what's I to the 100?
1.
1? How did you do that?
Because it's a factor of 4.
Because 100 is a factor of 4. So we could rewrite I to the 100 as I to the 4 to the 25. And I to the 4 is 1. And 1 times 1 times 1, 25 times is still just 1. Alright, so let's try another one. What's I to the 1002?
Negative 1.
Negative 1?
Yeah.
Mm-hmm.
How are we doing that one?
With the 2.
Well, I to the 1002 is equal to I to the 1000 times I to the 2, right?
Oh. Mm-hmm.
And I to the 1000 is 1, because 1000 is a multiple of 4. I to the 2 is negative 1. 1 times negative 1 is negative 1. Good?
Mm-hmm.
Okay, so there's our quick recap with I. Now let's remind you about what a complex number is. So let A and B be any two real numbers. Get so far?
Mm-hmm.
Don't forget our notation. That's a little N symbol, drew that kind of small. NR. Then A plus B times I is called a complex number. We call A the real part, and we call B the imaginary part. You with me? Now notice that for any real number A, pick any real number A that you want. A is also equal to, right up here, A is equal to A plus 0I, right?
Yes.
So A was a real number, A plus 0I is a complex number, so every real number is a complex number. So the real numbers are a subset of the complex numbers. Every real number is complex. Not every complex number is real. Go ahead.
So that means complex numbers has a bigger infinity than real numbers. What's that?
We won't talk about that. But to show you how that doesn't necessarily follow, think about it this way. The integers are a subset of the rationals. Yet the two sets have the same size, same cardinality. So being a subset doesn't mean you're smaller. Even being a proper subset doesn't mean you're smaller. Anyways, so the real numbers are a subset of the complex numbers. So to just write down our sets of numbers that we have so far, so we start out by talking about the natural numbers, which were 0, 1, 2, 3, 4, 5, 6, etc., are a subset of the integers. The integers now include the negative whole numbers as well. Negative 3, negative 2, 1, 0, 1, 2, 3, 4, 5. So every natural is an integer. Every integer is a rational. I can represent any integer as a fraction. Pick any integer, like 7. Write it as 7 over 1. Okay, now it's a rational. Every rational is a real. And then we just really showed that every real is a complex. Good with that chain there?
Yeah.
Okay. For the majority of the class, we'll just be talking about real numbers, not complex numbers. They kind of come in and out of the conversation as we go through the class. Anyways, okay. So how do we add two complex numbers together? So if I have a complex number, a plus bi, and I have some other complex number, c plus di, what do I get when I add them together? Pretty easy. Add the real parts together. So a plus c are your real parts, and then add your imaginary parts together. If I have bi and I add di, then I have b plus d i's. That one make sense?
Yeah.
Yeah.
That was pretty straightforward. Here's one that's not as obvious. What if I have a plus bi times c plus di? Well, then I have ac minus bd plus bc plus adi, right?
Wait, why the minus?
Why the minus? Wonderful. So let's prove that one really quick because it's not as obvious. And we're just going to multiply it out the same way that you know and love. So a plus bi, c plus di. So I'm going to multiply this out. So a times c, right there. A times di, right there. Bi times c, right there. B times di, or bi times di, right here. Good so far?
No, I see. Yeah.
Now, I'm just going to change the order as I write these first. So I'm going to write my AC term first, and then I'm going to move this term right here. But what is I squared?
1.
Negative 1. So I'm going to replace I squared with negative 1. So this term's right there, this term's right there, this term's right here, this term's right here. To these two terms, I just factored out the I. Good? And then AC plus BD times negative 1 is the same thing as AC minus BD. Right? And then that term I just rewrote right there. And we're done. That's our proof. Just really showed that that's equal to that. This is what we were showing. Good? And so yeah, that minus sign comes from the fact that somewhere along our way we're going to have an I squared. I squared comes out as negative 1.
Okay.
Wonderful. All right, so let's do some exercises then. So let's look at negative 5i squared. What is it?
25.
25.
Negative 25.
Negative 25. So when we square this, we get negative 5 squared times I squared. You apply the square to everything. Negative 5 squared, that's 25. I squared, negative 1, so we get negative 25.
Oh, yeah.
All right, let's look at that next one. Well, I get right there. Ooh, will my chair fit? Nice. All right. Multiplying this out, 3 times 2, that gives us 6, right? Then we have 3 times negative 6i gives me
Negative 18i.
minus 18i. Then we have 5i times 2 gives me plus 10i. And then 5i times negative 6i gives me
30.
negative 30, right?
No.
No.
No, positive 30. Right? Okay. And then, so now we just add like terms. So we add our real parts, we add our imaginary parts. That gives us our resulting complex number. So we have 36 minus 8i, right?
Mm-hmm.
All right. Now, if p is greater than 0, so it's a positive number, then what is I times the square root of p squared equal to?
Just negative p.
Just negative p. So we're going to square both of these. So I squared is I squared times square root of p squared is p. And then negative 1 squared is just negative 1, so that gives me negative p. Good? Okay. So then, what are the square roots of negative 5?
What do you mean?
What are the square roots of negative 5? What is a square root of a number? It's something such that when you square it, you get the number. Can you come up with a number such that when I square it, I get negative 5?
Square root 5 times
I times the square root of 5. Right? If I square that out, I'm going to get negative 5.
Oh, I see.
Can you think of another one?
Negative I times the square root of 5.
Negative I times the square root of 5. There's another one.
What?
You stuck on this one?
Where does the negative go on the I?
Where does that negative go?
Yeah.
When you square it, turns into 1.
Oh. Yeah.
When you see it, let's multiply that one out. So we have negative I times the square root of 5 squared. That's equal to negative I squared times the square root of 5 squared, or we'll just put 5. Good so far?
Oh yeah.
Okay. So this is equal to 5?
Negative 5.
Negative 5. So this is the square root of negative 5. And our other square root was without the minus sign. So those are the two square roots now of negative 5. And notice that we can now make sense of square roots of negative numbers. And just like 5 had 2 square roots, now negative 5 also has 2 square roots. Make sense?
Yeah.
Probably should have done negative 4 instead. Let's think about that one, because then we can think about the counterpart. So if I say, what are the square roots of 4? First off, we'll say positive 4. What are the square roots of 4?
2. Negative 2.
And negative 2. It only has 2 square roots, 2 and negative 2. Now when I say, what are the square roots of negative 4?
Yeah.
They're 2i and negative 2i.
Oh. Yeah.
Make sense? I see one where we could actually calculate the square roots. Writing what we had before, we said it's going to be I times the square root of 4, and it's going to be negative I times the square root of 4.
Okay.
But the square root of 4 is just 2.
Yeah.
So 2i and negative 2i. That make sense now?
Mm-hmm.
Wonderful. All right, let's do another example. Let's calculate this square root. The square root of negative 4 times negative 6.
Don't you have to convert the roots of the negatives to the counterpart with I?
Yeah, we can put i's in here if we want. So the square root of negative 4i, or the square root of negative 4 is the same thing as I times the square root of 4, right?
Yeah.
It is?
Because it's negative 1 rooted.
The square roots of negative 4
Oh.
were I times the square root of 4 and negative I times the square root of 4. Those were its 2 square roots.
Okay.
Okay, so square root of negative 4 is the same thing as I times the square root of 4.
But square root of 4 is just 2.
Well, let's do this one really quick.
Okay.
Times I times the square root of 6. Right? And now, with what you just said, we know that I times I is negative 1, and the square root of 4 is just 2. So this is equal to negative 2 square roots of 6. Good?
Isn't there's like a shortcut that I learned in elementary where you can just like multiply what's inside each radical and then put them under one radical. You multiply them together. And that comes out positive what you got. So does that shortcut just not work when you're dealing with negative radicals?
The problem that we're going to have is when we take the square roots, there's multiple solutions. So notice that the square root of negative 4, I could have used, there's two solutions. Negative 4 has two square roots. It has I times the square root of 4 and negative I times the square root of 4. Similarly with square root of negative 6, as I times the square root of 6 and I times negative square root of 6. And if I would have picked the negative for one of those, it would have taken the negative out of that. So this is one of the solutions.
Oh, okay. That makes sense.
Yes. Goes back to, and for the rest of you, if I kind of lost you on that, don't worry about that yet. We'll make that more clear as time goes on. But that goes back to the heart of that problem that I often show people for showing that 1's equal to 0, or 1's equal to negative 1 or something like that. Can't remember what it is.
No.
It's basically using that exact confusion. That's the heart of the problem. We'll look at a different proof today that 1's equal to 0. One that's not as subtle. We'll get there. Don't worry about it yet. I know you're curious.
You already showed that to us. Most of us.
I don't think I showed you that one, because I just went and found a random one. I showed you that 1's equal to negative 1. Anyways, we'll get there. Back to this. So now let's talk about roots. So R is an nth root of A, provided that R to the n is equal to A. That's what we mean by an nth root. That make perfect sense? 2 is a square root of 4, because 2 squared equals 4. 2 is a fifth root of 32, because 2 to the 5 equals 32.
Gotcha.
Negative 2 is a fifth root of negative 32, because negative 2 to the 5 equals negative 32. Good?
Yeah.
Okay, so that's what we mean by an nth root. So let's look at an example. Now, we're going to prove this down the road, but in general, if we're talking about the square roots of a number, there's 2 square roots. If we're talking about cube roots of a number, there's 3 cube roots. If we're talking about the fourth root of a number, there's 4 fourth roots. And we'll deal with that down the road, but just giving you a piece of it now, really quick looking at cube roots of 8. There's 3 cubed roots of 8. What are they? They're 2, negative 1 plus the square root of negative 3, and negative 1 minus the square root of negative 3.
What?
Those are all the cubed roots of 8. And you're saying what, so you don't like one of the ones I've drawn up there. So let's write it out. Let's see, we're done with stuff over here.
And just, how do you get the...
Yeah,
how do
let's
you
just
get
multiply it
multiple
out.
roots? Okay.
So we'll pick that one. That one and that one aren't going to be much different.
Mm-hmm.
Shouldn't matter which one we do. So I'm looking at negative 1 plus the square root of 3 times I is the way I'm going to write that.
Okay.
And I'm going to look at this cubed. Right? So first thing I'll do is I'll multiply the, well, that cubed is equal to, let's multiply this by itself. Let's see, negative 1 times negative 1 is
1.
1. Negative 1 times that is negative square root of 3i.
Okay.
Maybe I'm losing you here. Let me just write this out all in one. So we're looking at 1 minus the square root of 3i times 1 minus the square root of 3i times 1 minus the square root of 3i. Right?
Isn't it negative 1 plus the square root of 3i?
Is that the one we're doing?
Yeah.
Oh,
You got it mixed
thank
up.
you. Negative 1 plus, negative 1 plus, negative 1 plus. Good catch. Okay, so multiplying these two together. So I did negative 1 times that. I did negative 1 times that. Now I'm going to do square root of 3i times that. So that's going to be minus square root of 3i again. And then that times that is going to be what?
-3.
Negative 3. You with me?
Mhm.
And we still have negative 1 plus the square root of 3i over here. So I just multiplied those two together right there.
Mhm.
Simplify really quick. So we got, keep our parentheses here. We got 1 minus 2 square root of 3i minus 3. Well, combine those together actually. So negative 3 and 1, that's negative 2. So we have negative 2, why am I doing a comment? Negative 2 minus 2 square root of 3i. Okay. And we're going to multiply this by negative 1 plus the square root of 3i. Right?
Mm-hmm.
Okay. So now this is equal to negative 2 times negative 1 is going to be 2. Negative times that is going to be plus 2 square roots of 3i, right?
Mhm.
That times that is going to be minus 2 square roots of 3i. And then that times that is going to be, the i's squared is going to give me negative 1.
Mhm.
But it cancels out with your
Cancels out with the negative 2, gives me a positive 2.
Mhm.
So I have 2 times the square root of 3 times the square root of 3, or 2 times 3, or 6,
What the heck?
So it's 8.
which is equal to, crazy, 8. Because that I cancels out with that. This term cancels out with this term. So we have 2 plus 6. Okay? And you'll learn how to calculate these. And that will be like in the middle of the class, or closer to the end of the class. But the point is, it is a cubed root of 8. So here are all the cubed roots of 8.
Mhm.
Okay, so now we have a notion, since we just barely ran into some ambiguity. When we're talking about the cubed root of 8, so if I were to write on the paper, let's look at the cubed root of 8. How do you know which of these numbers to assign to it? When I talk about the cubed root of 8 on a paper like that, am I talking about this number, or this number, or this number?
Does it matter?
Yes, it does matter.
Your first one.
So, yes, it seems more natural for some reason for it to be talking about 2 than either of those numbers, right? And so we have a notion of the principal nth root. And that is what we mean when you see the nth root of some number a. We are talking about its principal nth root. So 8 has 3 cubed roots. The principal cubed root of 8 is 2.
Because it's smaller?
Huh?
Because it's smaller?
No, not because it's smaller. So we'll give you the rule really quick for it. So here's the rules for how you determine the principal cubed root of 8. First of all, if a is a number greater than 0, the principal root is the positive real root. We already showed that every single positive number has 2 real square roots, one positive and one negative.
Yes.
That was for square root, sorry.
Mhm.
So any positive number, when you look at its roots, it always has at least one positive root. So when you look at the square root of 4, that was 2 and negative 2. 2 is its principal square root. When you look at the cubed root of 8, it were these 3. This is its positive real root.
So all of them only have one positive root?
Yes. Every single real number greater than 0. If you take its nth root, whatever n is, it will always have one, and only one, positive real root. Okay?
Mhm.
If a is equal to 0, then its root is just 0. Because those are all the roots of 0. It's always 0.
Okay.
Okay? Now, if a is less than 0, and n is odd, then the negative real root is the principal root. So, for example, when we look at the cubed roots of negative 8, for example, so if we were looking at the cubed roots of negative 8, one of them would be negative 2, and then we'd have 2 other complex numbers.
Mhm.
Negative 2 is the principal cubed root of negative 8. So if we have an odd number here, and it's negative here, its principal nth root is the negative real number, not the complex number.
Okay.
Okay, so we have one more case now. What about if a is less than 0 and n is even?
Then it's
Then any root you pick works.
So then it doesn't matter?
So then it doesn't matter. So then the principal root can be referring to any of them. We don't really work with those in this class. Because at that point, it only has complex roots.
Oh, yeah.
So if we were talking about the fourth root of -8, those are only complex roots. It doesn't have any real roots. They're all complex. So at that point, the notion of a principal root kind of breaks down.
Okay.
So you'll notice that it'll be kind of contrived throughout this class that we avoid situations like this. Okay. So, notation, the nth root of A signifies the principal nth root of A. It'll just be understood that anytime n right there is an even number, then A is also an even number. And that's just an agreement between us and the author. The author explicitly says, we're just going to make that assumption.
Okay.
Okay. So then some examples that we already talked about. So now the principal cubed root of 8 is 2. The principal cubed root of -8 is -2. The principal square root of 4 is 2. With me?
Mm-hmm.
Now, when I write the symbol, and I don't bother to put my n in there, it's assumed that it's a 2. So not writing it is the same as a 2 being right there. Good?
Yeah.
All right, so some exercises for you. What's the principal fourth root of 81?
3.
3? You positive?
Mm-hmm.
3. And the principal square root of 16 is 4. And now I'm going to get bored of saying the principal square root over and over again, and I'm going to be lazy and just say the square root of 16 is 4.
Okay.
And that's how I'm going to read it from here on out. You're going to say, what about -4? I'm going to say, we're talking about the principal. Stop making me repeat that. Okay. Now note, by definition, when we say the nth root of A, we mean the number such that when you raise it to the power of n, you get A.
Mm-hmm.
What's the square root of 9? It's a number that when you square, you get 9.
Mm-hmm.
The nth root of A is the number such that when you raise it to the nth power, you get A. So by definition, if we take the nth root of A and raise it to the nth power, we always get back A, by definition.
Mm-hmm. Okay.
Anything weird about that?
No?
Okay. So then let's do some more really hard examples. Oh, I just filled it in for you because it's so obvious. So if I take the fourth root of -3 to the 4, I get -3. If I take the square root of 2 squared, I get 2. If I take the sixth root of ACB squared to the power of 6, I get ACB squared.
Mm-hmm.
Pretty obvious?
Yeah.
Okay, properties. We just already said it.
Mm-hmm.
The nth root of A to the n is always equal to A. Now, other way around. Notice that now I'm going to put the n on the inside. The nth root of A to the n is equal to A. And note, by our agreement with the author, A is greater than 0 if n's even.
Okay.
Yeah.
So anytime you see that, you can assume if n's even, A was a number greater than 0. That's our agreement with the author.
Mm-hmm.
So from here on out, we're going to assume that this is always the case,
Are we gonna?
and we're going to assume that A was a number greater than 0 if it turns out our n is even.
What do you mean that's an agreement with the author? Like,
The author explicitly says, every time I use this notation, unless otherwise specified, I'm doing this when n is even.
why? Do you
So that it has a principal square root. Because the principal square root, or the principal fourth root of -8 doesn't exist. There is no principal fourth root of -8. It's not defined.
Alright.
So he says, since we're using this notation to specifically talk about the principal's root, I promise not to give you scenarios where it doesn't actually talk about the principal root. So you don't have to get confused by that.
Okay.
Okay, so more properties now, like Emma was just talking about. The principal nth root of A times B is the same thing as the principal nth root of A times the principal nth root of B.
Mm-hmm.
And the principal nth root of a over b is equal to the principal nth root of a divided by the principal nth root of b, as long as b is not 0. Why b? Why do we require b not equal to 0?
Because that's unidentified. If it's something over 0.
Because then we'd be dividing by 0, which isn't allowed. Unidentified. You can't identify it with anything, because it's undefined. Kind of works. Okay. And then finally, we'll prove this last one, but you probably already have good intuition for this. If we talk about the nth root of a to the m, that's the same thing as a to the m over n. You've probably come across that before. In case you haven't, let's prove it. So the nth root of a to the m, I'm going to prove that that's equal to a to the m over n. You with me? Okay, so first off, let x equal this thing, and I'm going to show that x is also equal to this thing.
Okay.
Now, by definition, what is this thing? What is the nth root of a to the m? It's the number such that if you raise it to the power of n, you get a to the m. Did I lose you in that? Was that a word sandwich? Let's draw over here so I can say it again. When I said something like, what is the cubed root of 8? You know that this is equal to 2. How did you know that? You knew that because 2 cubed was equal to 8.
Yeah.
Okay, so by definition, the cubed root of 8 is the number such that when I raise it to the power of 3, I get 8.
Say that again. I thought 3 was.
By definition, the cubed root of 8 is the number such that when I raise it to the power of 3, I get 8.
Oh, yeah. Sounds like a log. Yeah.
No, not a log. So, by definition, the nth root of a to the m is the number such that when I raise it to the power of n, I get a to the n. So I am saying that I am going to show that x is the nth root of a to the n. Or in other words, I'm going to show that x to the n is equal to a to the n. And I'm done.
Yes, that makes sense.
Follow that logic there? Okay, so let's just show it and then maybe you'll just get it. So let x equal a to the m over n, and observe that x is equal to the nth root of a to the m if and only if x to the n is equal to a to the m. That's what it means for x to be the nth root of a to the m. It means that x to the n is equal to a to the m. That's what we mean.
Okay.
And if you follow that, that's the hard part of getting this proof. And then the rest is just obvious. So is everyone good with statement 1? Or do we need to see another example? You're good? Okay. So then let's show it. Let's show that x to the n is equal to a to the n. So then x to the n is the same thing as x. Remember, I said let x equal a to the m over n. So x to the n is equal to x to the n. Now, when you have an exponent to an exponent, that's the same thing as multiplying the exponents, right? So this is the same as this. Everyone follow me on that step?
Yep.
And then obviously the n's cancel out top and bottom, and we're left with a to the m over 1, or just a to the n.
Yep.
So I just basically showed that x to the n is equal to a to the n. Therefore, x is the nth root of a to the n. So therefore, x is the nth root of a to the n. So I said let x equal this. I showed that x is equal to this. Therefore, that's equal to that, because both of them are x. Follow that?
Yep.
Cool. And that's probably the hardest thing we have to talk about today. Okay, so now let's just do some examples. And make sure you got it. So the cubed root then of a to the 12 is equal to what?
A to the 4th.
A to the 12 over 3, which is a to the 4. That's using this right here. if you have the nth root of a to the m, it's a to the that over that. It's a to the that over that. Okay, so let's do the next one. What's the fourth root of 81 over 16? Well, we're going to use this property now. The nth root of a over b is the same thing as the nth root of a divided by the nth root of b. So the fourth root of 81 over 16 is the same thing as the fourth root of 81. The fourth root of 81 divided by the fourth root of 16. Oops. Fourth.
Let's see.
And what is the fourth root of 81?
3.
3. Because 3 times 3. Is that obvious to everyone that 3 to the power of 4 is 81?
Yep.
Because 3 to the 4 is the same thing as 3 squared times 3 squared, which is 9 times 9, which is 81. Okay. So this is the same thing as 3 over 2. 2 times 2 times 2 times 2 is 16.
Yep.
Good with that one? Okay, let's go on to the next one. The cubed root of 125y to the 9 over 8x to the 6. What's my numerator now going to be? Do it all in one go if you can. 5
5y to the 3
y to the 3 over
2x to the 2.
2x to the 2.
Yep.
Wonderful. Everyone see that? Cool. All right. Fifth root of this thing,
2y to the power of 3.
2y cubed. 2 to the power of 5 is 32. Y cubed to the power of 5 is 15. Good? Wonderful. Now we'll move our camera and continue on our merry way. Good enough. Okay. Oh, I guess we're still continuing. All right. So now, thinking about it backwards, what's 8 to the 1/3? 8 to the 1/3, if you work backwards, to help you think about this, let me erase that for a second. If you think backwards about this same property, which property was it? This one. 8 to the 1/3 is the same thing as the cubed root of 8 to the power of 1. Right?
Yeah.
And now, what is the cubed root of 8 to the power of 1? 2. You follow that?
Yep.
Okay. So now our next one was, let's look at -8, and then that's the whole thing to the 1/3. What's that going to be?
Negative 2.
-2. -8 to the 1/3 is asking the same thing as what's the cubed root of -8.
Yeah.
It's -2. Because -2 times -2 times -2 is -8. All right. What about 8 to the 2/3? Once again, we can think about this as the cubed root of 8 squared, right? Now, notice that we don't just always have to think about it this way. We can also think about it this way. I can also think about this instead as the cubed root of 8 and put the squared out there.
Okay.
And notice that that's easier.
Yeah.
Do you see why it's easier? Let's follow it this way for a second. So the cubed root of a squared, following this one, now we're asking what's the cubed root of 8 squared is 64, and what's the cubed root of 64? 4, right? But now let's do it this way. Let's find the cubed root of 8 and then square it. What's the cubed root of 8 squared?
4.
Which one of those was easier?
Right.
The top one. The top right one, right? So don't blindly just always use this. Remember that there's also this.
Okay.
All right? And so -8 to the 2/3 is
4.
4?
Negative 4.
-4?
Oh, it is 4.
They're saying 4, so it's 4.
Brett, this board can't use that logic.
Yes, it is, because negative 8 times 2 is 16. No, it's not. Negative 8 squared is 64.
Either way you square it, so that makes it positive.
Yes.
Yeah, notice that here we're going to run into trouble depending on how we interpret this. Because there's two ways that we can interpret this. You see this? So one way that we can interpret this is we can talk about this as the cubed root of negative 8 squared. Or we can talk about this as the cubed root of negative 8 squared. Those are the two ways that we can talk about this.
Well, either way, don't you get
And
the
either
same
way, it
number?
comes out the same.
Yeah.
So notice that in this scenario, it's probably easier to think about it this way than it is to think about it this way. So you leave your eyes out.
Yes.
But whichever's easier for you is whichever's easier for you. So if we think about it this way, we have negative 8 squared is,
64.
and the cubed root of 64 is 4. So this way we get 4. Over here, what's the cubed root of negative 8? Negative 2. Well, I guess that's not really that much harder.
Yeah.
I was thinking an I comes out, but then I realized we don't have evens there. And then square that, you get 4. So either way comes out 4, right? Okay. So this one was also equal to 4. So don't fall for the trap. When we did 8 to the 1/3, we got 2. So this one was equal to 2. But when we did negative 8 to the 1/3, we got negative 2, right? Now here we had 8 to the 2/3, we got 4. And when we did negative 8 to the 2/3, we still got 4. We didn't get negative 4. So putting a negative in front doesn't just switch what your root is.
That makes sense.
So actually work through it. Don't make that mistake. Okay, next one. 64 to the 5/6. Was that, huh?
No, 32.
32, but let's write out how we think about it. So we think about this as, probably the easiest way to think about this is the 6th root of 64, and then raise that to the 5, right? Because we don't want to do 64 to the 5 first, and then calculate it 6th root.
Oh, yeah.
64 to the 5, that'll be a nightmare. All right. So, what is the 6th root of 64? Probably just whatever you'd guess, 2. Right? 3 is too big, so 2. Why not? Yes, it turns out it's 2. So then we have 2 to the 5. And 2 to the 5 is equal to 32. And we could have done this the other way. We could have said it's the 6th root of 64 to the 5. But that would have been a nightmare.
Yeah.
What's 64 to the 5? That's going to be the 6th root of, let's see, 64 is the same thing as 2 to the 6. 2 to the 6 to the 5 is 2 to the 30. And then that's some big number.
What's up?
Yeah, that's going to be over 1 billion. It's going to be roughly 1 billion. And then so taking the 6th root of 1 billion, that's going to be tough. So a lot easier to do it this way. Okay. Any questions on those? You think it's something through? You questioning my billion approximation?
Yeah.
It's roughly 1 billion. It's going to be a little over 1 billion. You can take that to the bank.
Okay.
I work with powers of 2 a lot. We're on this one. You can just do 1024 cubed if you want.
Oh yeah, that would have been easy.
Okay. So now, note something that we already know. A to the p times a to the minus p, where p is some positive number, some positive integer. So a to the p times a to the negative p. What do we do when we multiply 2 terms together with their exponents? We add the exponents, right? When you multiply terms, you add exponents. What's p plus negative p?
Negative 2p?
0.
Oh.
You add them together. Positive p plus negative p is 0. So a to the p times a to the negative p is a to the 0. What's a to the 0? 1. We define that for any number not equal to 0, a to 0 is equal to 1. I'm not sure in this class if we define 0 to 0 equal to 1. Sometimes I do that. I can't remember for this class. Anyways, so a to the p times a to the minus p is equal to 1, right?
Okay.
So looking at this and this, ignore the middle for a second. If I divide both sides now by a to the p, I get this.
Oh.
Take this, divide both sides by a to the p, I get this.
That's how we get that.
Or if I take this and I divide both sides by a to the negative p, I get this.
It's kind of cool.
Is that straightforward enough? You can see those?
Yeah.
Okay. So yeah, there's where we get those pretty useful properties. So now let's do some simplifying. So I have 3a to the negative 2b to the 3 over c to the negative 3a to the 4. As a general rule, when we're doing algebra, we hate dealing with negative exponents, so we just make them positive. How do you make it positive? You flip it. So if I want to make that positive, I just put a squared down here, and if I want to make that positive, I put c cubed up here. So this is equal to 3, we no longer have the a squared, because we're going to move that downstairs. B cubed will keep upstairs, b cubed, times, and we're going to bring the c upstairs, c cubed, all over. Downstairs, we now brought the a down, so we have a squared, and then we also already had this a to the 4. With me?
Mm-hmm.
Which is equal to 3b cubed c cubed over a to 6. And that's how you simplify that. Good?
Yep.
All right, let's do a more convoluted example here. We're going to do negative 1 over 125 to the power of negative 2/3.
Okay.
So, first step is we probably want that to be a positive 2/3, right? So flip the reciprocal.
Okay.
So this is the same thing as instead of negative 1 over 125, I can write it as 125 over negative 1 to the minus 2/3. Or to the 2/3 now.
Oh, I see.
Does that step seem weird to anyone? Does it seem kind of weird? Or do you like it?
Before, so no.
You've seen it before, so no,
It
but
seemed
not.
like it made sense, and it made sense.
Let's write this out just a little bit more explicitly then. If we're not 100% like a duh, then we need to write it out more. So let's rewrite this. This is the same thing as negative 1 to the minus 2/3 over 125 to the minus 2/3. Right? Okay, yeah, just watch. Okay, now it's obvious. So it wasn't obvious before. Okay, so now let's make it obvious. So now I'm going to move that to the top, make its exponents positive, and that to the bottom, and make its exponent positive. So now I get 125. I like how you guys are all saying, oh yeah, now. Pretending like before, it wasn't oh yeah moment. Okay, so now we have that. And now factor out to the power of the 2/3, so I can rewrite this whole thing as just 125 over negative 1 to the 2/3. And so to go from here to here, I just flip the reciprocal.
You
Okay.
can further simplify that, right?
Yes, that was just step 1. Flip the reciprocal. Okay, which we can also do this as one more step. 125 divided by negative 1 is the same thing as negative 125 to the 2/3. Dividing by negative 1 is the same thing as multiplying by negative 1.
Mhm.
Remember that? Okay, so now, negative 125 to the 2/3. Do we want to square it first or take the cubed root first?
Take the cube root.
So we can take the cubed root and then square it, or we can square it and then take the cubed root,
Oh,
right? So what's the cubed root of 125?
5. Negative 5.
Sorry, yes, negative 5, because I meant to say, what's the cubed root of negative 125? So this is equal to, let's just probably write it out, the cubed root of negative 125, and then we're going to take that and square it. So the cubed root of negative 125 is negative 5, squared is 25. And so negative 1 over 125 to the power of negative 2/3 was really just 25. Good?
So weird.
So calculate that one, came out 25. Okay, now what's the square root of 147? Well, 12 squared is 144, 13 squared is 169. Okay, that doesn't work.
Yeah.
Save you whatever thinking you were probably doing there. Now what? Do we throw in the towel, say we're done? Yep. No! What else can we do to that thing? We can look at its prime factors
Of 147?
of 147.
Yeah, irrational numbers.
So 147, does that have any prime factors?
It doesn't have a 2.
2 doesn't go into it. What about 3?
It does have a 3.
It does have a 3.
3, how?
Well, 3 times 50 is
150?
minus 3.
Yeah.
Okay, so that was 49 threes. 50 threes got us to 150, so 49 threes gets us to 147. Ah, and 49, that's a prime number, right?
7,
No.
7.
No.
No, that's 7 times 7. Good? So now we can rewrite this as a square root of 7 squared times 3.
Oh, I see.
And then pull the sevens out.
Pull 7s out, but just to show us in the long way one so that we can justify pulling the 7s out from here on out, let's just do it the long way. I know that the square root of a product is equal to the product of the square roots. The nth root of a product is equal to the product of the nth roots. So this is the same thing as the square root of our first factor, 7 squared, times the square root of 3. And now, what's the square root of 7 squared? 7. So this is equal to 7 squared to 3. Is there anything weird in all that? Oh, sorry, go ahead.
Multiplying and add are way different, right? You can't pull it out if you're adding.
They are way different.
Okay.
Now, let me show you really quick. What's the square root of 4?
2.
2. What's the square root of 1 plus 1 plus 1 plus 1? Well, let's see. That's going to be the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1, which is 4. No!
Couldn't you square it
Yeah.
all in?
I can't break this up into the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1.
Oh.
Because that would equal 4. So no, I can't take that and go to that.
Okay. That makes
What
sense.
do you do?
You add the terms together
And then you have 4.
and then take its square root, which is 2.
Oh, it's not even 4. Okay.
No, it is not equal to 4. If we try to do this, then we get 4.
Yeah.
But the square root of 4 is 2. So I can't go from here to here. The bad step is you can't take a square root and just break it up into sums. That was the bad step. That's what you can't do. And no, it's none of our rules say we can do it. It only shows up with products. Good?
Yeah.
Okay. So this one came out to 7 squared to 3. Okay, let's look at the fifth root of this beast now. Well, we can rewrite this as the fifth root of 2 to the 6 times a to the 11 times c to the 9, right?
Yes.
Now I could break this up into a bunch of individual roots, like we did last time, or I could do what, can't remember who it was, said, and just realize that it takes 5 to pull one out.
Yes.
Takes 5 to pull 1 out.
So 2 to the 5
Oh, yeah.
means I can pull a 2 out, and I'll have 1, 2 inside.
Yep.
So see if everyone's okay with this step. If you're not, then we'll break it up more. If you're all okay with it, then we'll continue from here. So this is the same thing as 2 times the fifth root of 2 times a to the 11 times c to the 9. So I had 6 2's inside of here. I used up 5 of them to pull a 2 out. Because 2 to the 5, the 5th root of 2 to the 5 is just 2.
Why do you do that to only 2?
Well, I was going to do one at a time to make sure we were clear.
Yeah.
So when we're all said and done, the answer is 2 times how many a's? A squared times c, all times the square root, and we still have 1, 2, 1a, and 4 c's.
And it's the 5th root.
And it's 5th root, thank you.
Oh, I see.
5th root still. That's a 5. So we had 6 2's. We had to give up 5 to get 1 2 out. So here's 5 of them. Here's the last one. We still have 6 total. We had 11 A's. To get 1 A out, took 5 of them. To get 2 A's out, took 10 of them. So we have 2 A's here. We have 1 inside. This was 10 of them. That was 1. We still have all 11. Similar thing with C. Here's 5 of our C's. Here's 4 of our C's. So we still have 9 total.
Yeah.
Everyone follow that?
Yeah.
That's the algebra on that. Okay. So now let's just do this, I guess. So when we multiply 2 numbers together that have a part outside the radical and a part inside the radical, you just multiply it exactly how you would expect. Multiply the outside by the outside and the inside by the inside.
Okay.
Good? So what am I going to write here?
30 times root 2.
10 times the square root of 18. We'll do it one step at a time. Right? So we did the 2 times the 5 and the 6 times the 3 under the radical.
Yes.
And then 18, what's that? It's prime factorization. So this is 10 times 18 is the same thing as 2 times 3 times 3, right?
Yes.
2 times 3 squared. 2 times 9 is 18.
Okay.
And so now we can pull out the 3 and we get what Emma said, 30 square roots of 2. Any weird algebra happen there?
Nope.
Wonderful. So that was 30 square roots of 2. Alright, let's do this next one. Cubed root of a over b, all over the cubed root of b to the 5. What can we do here?
Combine the numerator and denominator into one cube root.
Perfect. We can look at this step in reverse. This is the same as this. So she's saying this is the same thing as the cubed root of a times b over b to the 5. Now what can we do?
Your b's can cancel out. Right?
We can cancel out 1b top and bottom. And so this is the same thing as the cubed root of a over b to the 4.
Okay.
Right? Huh?
Is it done?
You can play with it more if you want, but it's not going to get much simpler.
You can pull out a 1 over b.
Oh, that's a good point. Yeah, let's actually do that. So this is the same thing as, let's go back to how we had it written before, so we'll undo this step now. So this is the cubed root of a over the cubed root of b to the 4. Right?
Okay.
And then we can pull a b out on the bottom. And so now it's going to be the cubed root of a all over b times the cubed root of b. Oops, b with the 3 there, right?
Yeah.
And then probably the way that it would be given when it's all said and done is just 1 over b times the cubed root of a over b.
Okay.
Okay, so that was that one. What about this one? The cubed root of 3a plus 5 over x cubed. Where can we start with this one?
You can get a common denominator.
Get a common denominator under our radical. By the way, the name of the symbol right here is a radical. So when I say under the radical, I mean inside that symbol. So get a common denominator. What's my common denominator for these two terms? Huh?
X cubed.
X cubed. So I need to multiply this term, top and bottom, by x cubed.
Oh, yeah, of course.
You with me? So this is the same thing as the cubed root of, if I multiply this term top and bottom by x cubed, then I get 3ax cubed over x cubed plus 5 over x cubed. You follow that?
Yep.
Notice that x cubed over x cubed is,
Cancel out.
well, it's 1. So I multiplied 3a by 1, which doesn't change it.
Oh, yeah.
That's why that's a valid step. You can multiply a number by 1 as many times as you want. Doesn't change it. Okay, so now I have a common denominator, so I can write that all as one fraction. So this is equal to the cubed root of 3ax cubed plus 5 all over x cubed, right?
Yep.
All right, can we do anything else?
Cancel the x cubes.
Yeah, we can pull an x cubed out from the bottom. Oh, no, no, no. I cannot cancel that with that.
It's 1.
All right. If I have 2 plus 3 over 2,
Oh, this.
that is not equal to 3. I cannot just cancel out my 2's. 5 halves is different from 3. I happen to pick 2 that were close to each other. So, make another example more clear. 1 plus 1,000, or 10,000, over 10,000. This is basically 1. It is not equal to, oh, that's still getting close. Never mind, I just keep getting close. No, you can't cancel out sums. Should have done the same number. That's what I should have done. 5 plus 5 over 5, there we go, is equal to 2, right? Which is not the same thing as 5. That's what I should have done. Okay. Anyways, back to this one. No, we can't cancel out the cubes. But I can rewrite this as the cubed root of this over the cubed root of this.
Yes.
So I can rewrite this as the cubed root of 3ax cubed over, what's the cubed root of x cubed?
X.
Just x.
Where'd the plus 5 go?
Oh, I just forgot it. Thank you.
Can you take out that x cubed then on the top too?
Now,
For the same reasons.
there'd have to be an x cubed in this term, and then I could factor it out and then pull it out.
Yeah.
Good?
Yeah, that makes sense.
All right. And then our last one, multiplying this thing out.
Okay.
So let's multiply this out. Here, right on the other side. Square root of 2 times 2 square root of 2 gives me 4. Everyone follow that? Square root of 2 times 2 square root of 2. Square root of 2 and square root of 2 together gives me 2, times 2 gives me 4. Alright, so that was, we did this into this, now let's do this into this. Square root of 2 times 5 square root of 3 gives me 5 square root of 6.
Yep.
Remember that a product of square roots is the same thing as the square root of the product. So square root of 3 times the square root of 2 is the same thing as just the square root of 6. Okay, now let's multiply the square root of 3 into both those. Square root of 3 into that gives me 2 square root of 6. And then square root of 3 times 5 square root of 3 gives me 15? Yeah. So plus 15. And then so finally, collect like terms. For our terms without square root of 6, we have 19 of them, plus 7 square root of 6. Good? Cool. Okay, so the next concept that we're going to talk about is rationalizing the denominator. So oftentimes you're told to rationalize the denominator in an algebra course. What that essentially means is I don't want a square root in the denominator.
Yeah.
With me? So we're going to rationalize the denominator of the square root of 3 over the square root of 7. So square root of 3 over 7, that's the same thing as the square root of 3 over the square root of 7, right?
Yes.
And so we do have a square root in the denominator. We want to get rid of that. How can I make so that the square root of 7 is no longer a square root? What do I want to multiply by?
Square root of 7.
Square root of 7. So I'm going to multiply that by square root of 7. So I don't want to change my number, so I'm going to multiply by square root of 7 over the square root of 7.
Yeah.
That way I'm multiplying by 1.
Okay.
Now what is root 7 times root 7?
7.
7. And in the numerator we now have the square root of 21. And so the square root of 21 over 7 is the way we say that.
And that's rationalized?
And that's rationalized. Notice that the prime factors of 21 are just 3 and 7. So we can't pull anything out.
That makes sense.
Good? Let's do the next one. We have the cubed root of 3 over 4. So that's the same thing as the cubed root of 3 over the cubed root of 4.
Yeah.
What do I need to multiply the cubed root of 4 by to get just back to 4?
Cube root of 4 times 2 or square.
2 cubed roots of 4,
Yeah.
right?
No.
Yeah.
Because we need 3 of them to get 4.
Yeah.
So to be super explicit, we need to multiply by the cubed root of 4 times the cubed root of 4 all over the cubed root of 4 times the cubed root of 4, right?
Yes.
Yeah.
So we're multiplying by 1 still. Now the denominator, the cubed root of 4 times the cubed root of 4 times the cubed root of 4 is 4. And in the numerator, we can just multiply these numbers together.
Okay.
So it's going to be the cubed root of 4 times 4 times 3. I'm going to write it this way, 2 to the 4 times 3. You okay with that?
Yes.
So you can pull 2 out
So I can pull a 2 out,
and cancel out the 4.
which will help cancel out the 4. So I can write this as, we'll write down here. So I can write this as 2 cubed roots of 2 times 3 all over 4, right? Pulling out a 2. I have to eat up 3 of them to pull out a 2, leaving 1 in there. And then 2 over 4 is the same thing as just 1 over 2. So this is the cubed root of 2 times 3 now. We'll just put a 6. We won't be able to do any more with that, over 2. And that's how you rationalize the denominator and simplify it.
Okay.
Okay. Now, the beast. We might need more space for that, so let's actually get some space over here. So for that one, we have 3 square root of 2 minus the square root of 3 all over 2 square roots of 2 minus the square root of 3. How on earth are we going to get square roots out of the denominator of this thing?
Times it by itself.
We times that by itself?
Yes.
That won't get us there. Has anyone done a problem like this before?
If you multiplied it by root 3, you can cancel it out.
If I multiply top and bottom by the square root of 3,
Yeah.
so if I multiply top and bottom by square root of 3, that's going to be equal to, distributing that in, we're going to get 3 square roots of 6 minus 3 all over 2 square roots of 6 minus 3. And we still need to get rid of that square root of 6. Now what are we going to do? If you multiply by square root of 6, you'll get rid of it there, but then you got it back on that term.
Oh, what the heck?
Okay, what the heck? So now, we multiply by what we call the conjugate. Alright, so let's do a little bit about the conjugate, then come back to this. the conjugate, if you see a times the square root of b plus c times the square root of d, the conjugate of that is what you get when you just put a minus sign there.
Oh, we do this for calculus.
We did do this for calculus. So let's just write this out really quick with just variables, and I'll write a little bit smaller so we don't go too far. So let's look at a times the square root of b plus c times the square root of d. And let's take that and multiply it by a times the square root of b minus c times the square root of d. And the amazing thing is when we do this, all our square roots are going to cancel out. That's the amazing thing that's going to happen. Okay, so let's see that. So this is equal to, that term to that term, what do we get? We get a squared times b. You see that? Multiply this to this, we get negative ac squared to b. Right?
Wait,
Mult-
where did your b go?
Oh, thank you. Square root of BD. Yeah, when you both. Square root of BD. Thank you. Multiplying that to that, right? Okay. Now multiplying this to this, what do we get? Plus AC square root of BD. And then multiplying this to this, what do we get?
C squared.
Negative C squared times D. And notice that the terms with the square roots in them cancel each other out.
Yeah, that makes perfect sense.
And so, when it's all said and done, you don't have any terms with square roots in them anymore. So, the conjugate of this is this. The conjugate of this is this. You just flip the plus to a minus or a minus to a plus.
Yep.
That's what you mean by the conjugate. And so, you'll often hear when you come up with a problem like this, they'll say, multiply top and bottom by the conjugate of the denominator. So we're going to multiply top and bottom by the conjugate of this thing. So we're going to multiply top and bottom by 2 square roots of 2 plus the square root of 3 over 2 square roots of 2 plus the square root of 3. And the amazing thing is going to be that our denominator is not going to have any square roots when we're done. So this is equal to, we need to put parentheses there to help us think. We'll do our numerator first. When we multiply these two together, what do we get?
6 squared is 4.
Which is
12.
12, right? 3 times 2 is 6, root 2 times 2 is 2, 6 times 2 is 12.
Yep.
Okay, so that was that times that. This times this gives me
3 root of 6.
3 square roots of 6, but this times this gives me,
Negative 2 roots of 6.
so we're going to have 3 square roots of 6 minus 2 square roots of 6 gives me plus 1 square root of 6, right?
Yeah.
Yeah.
You follow that? And then negative square root of 3 times positive square root of 3 gives me
Negative 3.
negative 3. Okay, now let's look at these ones. 2 square roots of 2 times 2 square roots of 2 gives me
8.
8. 2 square roots of 2 times the square root of 3 gives me,
2 squared is 6.
and this gives me
2
Negative 2 squared.
negative 2 square roots of 6. So we get 2 square roots of 6 and negative 2 square roots of 6. Those two cancel. And then finally we have minus 3. So this is equal to 12 minus 3 is 9 plus the square root of 6 all over 5.
Okay.
And that's how we simplify that one. Good?
Yep.
Cool. All right. Now, radicals to rationals, I guess. So if we have the cubed root of the fourth root of 3x to the y, or the cubed root of the fourth root of 3xy, what's that equal to? Sometimes it's easier to think about these when we think about them in terms of their exponents rather than in terms of radicals. So remember that the cubed root, if I say the fourth root of x, that's the same thing as x to the 1/4, right?
Okay.
So this is the same thing as the cubed root of 3xy to the 1/4. Right?
Yes.
And then once again, the cube root of something, that's the same thing as raising it to the 1/3 power.
Yes.
And so, if I have this raised to the 1/3, what do I have? I have 3xy to the power of what? 112. Yeah, 1/4 times 1/3 is 112.
Okay.
So sometimes it's harder to think about it this way and easier to think about this way. Okay, let's try another one. 2 times the cube root of 5x to the 4.
Oh.
So distributing the 4, 2 to the 4 is still just 2 to the 4. And then this we can think about as 5x to the 1/3 times 4 is going to be times 5x to the 4/3. You see that? Or did I do too many steps in one go?
I see it.
You good? Wonderful. All right, let's look at this one. So this one is going to be 4 to the 1/3 times b to the 2/3 times x to the 1/3 all over. Notice that there's nothing there, so this is 2 to the 1/2. 3 to the 1/2 times a to the 1/2 times b to the 1/2. You follow that?
Don't you want to get the 1/2 out though?
Now, notice that I have a b here and a b here. I want to combine those somehow. Right?
Mm-hmm.
So I want to move the b upstairs. If I move the b upstairs, what does that do to its exponent?
Makes it negative.
Makes it negative. So this is the same thing as 4 to the 1/3 times b to the 2/3 times b to the minus 1/2 times x to the 1/3 all over 3 to the 1/2 a to the 1/2. Right? And then finally I can combine the b's. And when I combine the b's together, what do I get? 2/3 minus 1/2 is what?
1/6.
1/6.
Yep.
4/6 minus 3/6 is 1/6. So I'll replace the b with a 1/6 and we're done. Good?
Oh,
That's all you're doing. What about the other halves you're trying to?
yeah, don't you want to get the
We can't
halves out?
combine any of the other terms
Oh,
together.
it's not rationalizing denominators.
Oh no, I'm not rationalizing the denominators on this one. I'm just showing you how we go from radicals to rational exponents.
Okay, gotcha.
And why it might be useful to see how that b and this b interact and how you can cancel them. Okay, let's do the next one. The 6th root of 25w to the 4. So this is the same thing as 25 to the 1/6 times w to the 4 over 6, right?
Yes.
Which is equal to 25, we can rewrite that as what?
5.
5.
5 squared. So 5 squared to the 1/6 is the same thing as 5 to the 2/6, right?
Yeah.
Times w to the 4/6 is the same thing as w to the 2/3.
Okay.
And then finally, 5 to the 2/6 is the same thing as 5 to the 1/3. So 5 to the 1/3 times w to the 2/3. And if I want to get back into this same radical, then I can rewrite this as now a cubed root of 5 times w squared. So the 6th root of that is the same thing as the cubed root of that.
Oh, yeah, that makes sense.
Makes it a little simpler. Good?
Mm-hmm.
Okay, just tell me this one. If I take the 5th root of the 3rd root of u, I get u to the 15,
1 over
1/15th.
Yes, yes.
U to the 1/15th. All right. And then let's do this one. So the cubed root of a squared is the same thing as a to the what? Just rewriting this term. 2/3. Times, what's this one?
3/4.
3/4. Which is equal to, now what do we do?
Multiply, add
Add the exponents. So now you need to do 2/3 plus 3/4. What do you get?
17.
10 twelfths?
12, 8.
2/3 plus 3/4 is definitely more than 1. So if you eat 2/3 of pizza and then you eat 3/4 of pizza, you definitely ate more than one pizza. So sanity check there. 5/3?
Is that wrong?
Oh yeah, okay.
It's pretty tricky, guys. 2/3 plus 3/4. You gonna make me write it out? What's our common denominator? 12. So this is equal to, how many twelfths is this?
8.
8 twelfths. Multiply top and bottom by 4. 8 twelfths. Plus multiply top and bottom by 3. 9 twelfths is equal to 17 twelfths. Can we reduce that? No. 17's prime.
Oh yeah.
18 twelfths we could reduce it. 15 twelfths we could reduce it. 16 twelfths we could reduce it. But that pesky 17. It's prime. Can't reduce it. Okay, so the answer is 8 to 17 twelfths. That was going to be on the test, by the way. Exactly. You have to say it out loud. Maybe some people were worried. Nothing. Okay. So now moving into the next section, and we're going to introduce equations now. Start doing algebra with some equations. You probably heard about an equation before. What's an equation? An equation is a statement that two numbers are equal. Here's an equation. Here's an equation. This equation is true. This equation is false. They're both statements saying that two numbers are equal.
Yeah.
That's what an equation is. Good so far? Okay. Now we have a notion of an open equation. An open equation is one containing at least one variable. Here's an open equation. Here's an open equation. Good? Now notice that when you have an equation, its truth or falsity depends on the variable x when you have an open equation. Some values of x make the equation true, other values of x make the equation false. If I plug in 5 for x, it's false. If I plug in 2 for x, it's true in this particular equation. Right?
Yes.
So now we have a notion of what we mean by a solution to an open equation. What's a solution to an open equation? A solution to an open equation consists of a value for each variable in the equation such that the substitution makes the equation true. So 2 is a solution to this equation because when I plug in 2 for x, it makes that equation true. I don't know a solution to that equation. I'm not going to think about it. But there is one. Some x, some y that makes that true.
I have a question. So is an open equation not technically an equation because it's not a statement?
Correct. Because you can't call it one. To go back to our terminology, this is an indefinite predicate. And it takes a quantifier or a substitution to make it a statement.
Right.
Okay, yeah. Let me do another one here with values that are easier to do in our head. Let's say y is equal to 2 plus x. Okay, so this one has 2 variables. What's an example of a solution to this?
Y equals 5, x equals 3.
Yeah, y equal 5, x equal 3 is an example of a solution. How many solutions are there to this equation? 1, just 2. How? Huh?
You gotta count it if it's like 1 plus 1. X equals 1 plus 1.
That's the same thing as 2.
Yeah.
So we already counted it.
Okay.
How is there 2? Oh, you're saying x is 2. Okay,
2 is the only solution. There is one solution, namely 2,
yeah.
to this open equation. There's only one number x I can plug in there that makes it true. All other values make it false. Okay. Over here, how many solutions are there?
Infinite.
2.
Infinite. For any x you choose, I can always find a y that makes it true. Pick any x you want. We'll pick pi. What's the y that makes it true? 2 plus pi. Whatever number that is. 5.14159, blah, 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 blah. Take x equal to 19, then y equal to 21 makes it true. So y equal to 21, x equal to 19 is another solution. So, some open equations have infinitely many solutions, sometimes they don't. Okay, so let's read this again, and I think that will cement it in your head, and we'll be good. A solution to an open equation consists of a value for each variable in the equation, such that the substitution makes the equation true. To solve an open equation means to find the set of all solutions. That's what it means to solve the equation. Make sense? And you've been told to do that 100 times in school. That's exactly what it meant to do. Find the set of all solutions. Okay, so example, 3x plus 5 equals 11. And let's say that our job is to solve it. What do? We can subtract 5 from both sides. So we can say that 3x and, I'll stand over here. So we can say 3x is equal to, what's 11 minus 5? 6. And then we can divide both sides by 3 and we get x is equal to 2. And that's the only solution. So our solution set in this case looks like this. Right?
Yes.
That's a set of all solutions. Alright, let's look at another one. 2x minus x equals 1. Now what do?
Like to simplify the equation.
To solve it. We're looking for the solutions to this equation. What values of x make it true? How do you typically solve equations like this?
Combine like terms.
Combine like terms.
Yes.
We collected all our x squared, we collected all our x, we collected all our constants.
I started with 1, that's right.
Can you start by adding x to both sides? And then divide?
Easier to just move the 1 over. So when you see something like this, typically first step we do is we put everything on one side and 0 on the other side. You guys seem a little bit stumped by this. 2x squared minus x minus 1 is equal to 0. Right?
Yes.
I subtracted 1 from both sides. Now what can we do with that?
Factor it.
Factor. You guys have done basic algebra before. I mean, I know I'm teaching you algebra, but it's assumed that the majority of you have done algebra before. And then we factor this. How on earth are you going to pass physics if you can't solve these equations?
That's a really good question.
So we're going to factor this, and it's going to be 2x times something and x times something equal to 0, right?
Mm-hmm.
So I need to find two numbers here. Their product is -1. And then when we do their sums, we get negative x. So what's it going to be?
-1.
-1 here or +1 here?
Plus 1 there.
+1 here, -1 here.
Okay.
You see that? -2x plus x gives me -x. -1 times 1 gives me -1. 2x times x gives me 2x squared. Anyone confused by that? Okay, so what are my solutions? What x's make this equation true? 1/2 and 1. Almost.
-1.
-1/2 and 1.
Yes, -1/2.
A product can only equal 0 if one of the terms in our product is 0. So either this has to be 0 or this has to be 0. When is this term 0? When x is 1. So 1 is one of our solutions. And when is this term 0?
Next is -1/2.
If I know that 2x plus 1, if I want that equal to 0, then I need 2x equal to -1, or I need x equal to -1/2. So, our solutions are 1, -1/2. That's our solution set. That's what meant by solve this equation, right there. 2x squared minus x equals 1.
Okay.
Okay. Hopefully that was just a reminder, and now it's coming back to all you guys, and that looks stupid simple again.
Right.
And it's not one that we'd be puzzled by. Okay. Warning, 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 warning. Imagine I told you to find all the solutions to x plus 3 equals 2. And you started by multiplying both sides of this by x. Is there anything wrong with multiplying both sides of your equation by x?
Yes.
What's the problem? Let me help you see the problem first. What values of x make this true?
Just -1.
Just -1. So the solutions for this equation are just -1. Right?
Mm-hmm.
Now over here, what values of x make this true? If you plug in -1, it still makes it true.
Plug in 0.
But if you plug in 0, it also makes it true. So now solutions over here are 0 and -1. And notice that you just introduced a new solution by multiplying both sides by x. And a similar problem could have happened if you divide both sides by x. So imagine you start with the equation like this, and you said, first thing I'm going to do is divide both sides by x and get this. And then you solve for x and you get this. Now you lost a root. You lost a solution. So you cannot, always and forever, just multiply or divide both sides by some x. The only times that this is infallible and won't introduce solutions or get rid of solutions is if it's impossible for the thing that you're plugging in there or dividing by to be 0. If it can't ever be 0, you're good. If it's possible for it to be 0, you might have just added or gotten rid of a solution depending on what you were doing.
Okay.
Because if I have some equation and I multiply both sides by 0, then I found out that 0 equals 0.
What do you mean if it can't be 0? Like if the equation after you're done dividing or multiplying?
So if I took this and I multiply both sides by 5, then we're solid. Because 5 is guaranteed never to be 0.
Oh, I thought you were saying it's okay to multiply each side by x if it means...
It's okay to multiply both sides of your equation by some factor, as long as it's guaranteed that factor can never be 0.
And is that the case with x?
X, it's possible for x to be 0. We have no restriction from x being 0, and so that was the solution introduced.
I guess my question is, can you multiply both sides by x and then still have it like...
It depends on the domain of the function you're talking about.
Okay, fair enough.
So you could have potentially introduced a root. It's not a guarantee that you did. You could have potentially. So if you take something like this, multiply both sides by x, we introduce a root. Or if you start with something like this and divide by both sides by x, you just got rid of a root. I'm going to say root a lot, sorry. Root just means a solution to the equation. It has nothing to do with the square roots or cubed roots that we were talking about before. So, sorry, that's kind of a confusing word, but it's a word that's used a lot, so get used to it. When we talk about the root of an equation, we mean a solution to that equation. So, sorry that I keep saying that, but you gotta get used to it. Okay, so now that we've had our review, our warm-up problem, wherever it was, I think I erased it. Now we've had our warm-up problem, and we've had our warning, let's solve this thing.
Okay.
Okay, so I'm looking for solutions to this equation. What's the first thing I want to do?
Get everything to one side.
Get everything to one side?
Mm-hmm.
Yeah, we could do that.
Find common denominators.
Let's find a common denominator of everything first.
Okay.
There's no problem with getting everything to one side first. We could have, but I just want to get rid of our fractions. So what's a common denominator for all those things?
30 is one.
Does 2 go into 30?
Yeah.
Yeah. Just making sure no one's thinking in their head it has to be 3 times 2 times 10. Because the 10 already has a 2 in it. So it just had to be 3 times 2 times 5.
Yeah.
Which was 30.
Oh.
Okay.
So 30 is our least common multiple of 3, 2, and 10. Right? Okay. So I'm going to get 30 in my denominators everywhere. So what am I going to multiply this one top and bottom by? So it's denominator 30. 10. So I'm going to write this as 10x minus 40 over 30. We'll just put up, well, yeah, over 30. Sure, I'll keep the minus there for now. What's this one going to be now? 15x minus what? 45 over 30 is equal to 9 plus 3x over 30 minus 60 over 30. Now you might be thinking, didn't you just make that way harder, way uglier? Now what can we do?
Multiply both sides by 30.
Multiply both sides by 30. Wait, is it possible that we could be introducing a solution by multiplying both sides by 30?
I don't think so.
No, because it's guaranteed that 30 can never be 0. X can sometimes be 0, 30 can never be 0. So we're good.
Okay.
Okay, so now we get 10x minus 40. I may distribute that negative through, so we get minus 15x plus 45 is equal to 9 plus 3x minus 60. You with me?
Mm-hmm.
Now, just move everything. I'm going to move all my x's to the left and all my constants to the right.
Yep.
All right, so on the left we have 10x minus 15x minus 3x when we bring this over here. Everyone follow that, or was that too much?
So it's minus 8x.
10x minus 5 or minus 15 is negative 5. Minus 3 is negative 8x. Everyone good? That's all our x's?
Yeah.
Okay. Now we're putting all our constants over here. So let's see. We have negative 40 here. Plus 45 gives us 5. When I move it to the other side, it's now negative 5. Negative 5 plus 9 is?
4.
Minus 60 is?
Negative 4, 56.
Follow that?
Yeah.
Maybe think about it this way if it's easier. Negative 60 plus 9 is?
Negative 51.
Negative 51 minus 5. Negative 51 minus 5, negative 56. Good?
Yep.
All right, now what am I going to do?
Divide by negative 8.
Divide both sides by negative 8. Is that going to introduce a new solution?
No.
No, because negative 8 is never 0. That's impossible. So divide both sides by negative 8 and we get x is equal to 7.
Easy.
And that's our only solution. Good?
Yep.
Okay. So that's it for material. Now to introduce one thing to you as a quick test for you. We're going to go over a proof that 1 is equal to 0. Question, is 1 equal to 0? No, which means I'm lying to you. Now how am I lying to you? That's the question.
By saying no equals 0.
So-
This is a game.
Let's go over the proof. And your job is to figure out what's wrong with the proof. Now, when you see what's wrong with the proof, just raise your hand, don't shout it out. Okay, so I'm going to prove that 1 is equal to 0. All right, let a and b be real numbers such that a is equal to b plus 1. What are a and b? I have no clue. All I know is that a is equal to b plus 1. Are there two numbers a and b that make that true?
Yep.
Yes, so we're fine so far. For sure haven't cheated so far on this part. And then from here on out, you're on your own. I just don't want you to get confused by this line because that might seem weird to you. Okay, so just letting you know, this line is fine. We haven't cheated. Okay. So then, a minus b times a is the same thing as a minus b times a. Right?
Yep.
So, now I'm going to distribute the a into each of those terms. A times a is a squared. A times negative b is negative ab. That was distributing this out. Over here, a times b is ab. A times 1 is a. Negative b times b is negative b squared. Negative b times 1 is negative b. You follow that?
Yeah.
Just distributing. Okay, from here to here, all I'm going to do is subtract a from both sides. So a squared minus ab, wrote a minus a there. over here we had a squared, I'm going to skip that for now, minus b squared minus b, here's that a, and then minus a. So all I did going from this line to this line is subtract a from both sides. And a minus a just gets rid of the a's over here. So we have this is equal to this. You good? Okay. So now factor an a out of this and factor a b out of this.
Okay.
So when I factor an a out of this, we're left with a minus b minus 1. If we were to redistribute that a, we'd get a squared minus ab minus a. So just factor the a out. Over here we just factor out a b. So we get b times a minus b minus 1. Notice that we have a minus b minus 1, a minus b minus 1. So same factor on both sides, cancel those out, and we're left with a is equal to b. But remember what what a is. A is equal to b, but a is equal to b plus 1. So a equal to b is the same thing as b plus 1 is equal to b. Subtract b from both sides, we get 1 equals 0. Follow the proof?
Yeah.
Works, right?
No.
No. So my conclusion's wrong, so I must have tricked you. I must have cheated. Who thinks they know where I cheated?
I think I might.
I have an idea, but I don't know for sure.
You think you might, you have an idea, but you don't know for sure? Well, hopefully it's pretty obvious to you when you see the problem. Are you positive you know what the problem is?
Yeah.
Okay.
What's the problem?
What's the problem?
Problem is 1 equals 0.
The problem's right there. 1 equals 0. Were you working on homework and not paying attention to the proof? Do you know what we're doing?
Yeah.
I came up with the proof that 1 equals 0. You need to find the problem in the proof, because obviously 1's not equal to 0. So what's the problem in the proof? And just as a nice little life lesson for you on the side, by the way, think about how much education you all have in algebra. How many years have you studied algebra? Most of you, at least 3, right?
Give or take, yeah.
Give or take, yeah. And yet, here's a nice little simple thing, and if you weren't on your guard, you might be fooled with something as simple as algebra. So just because someone has a lot of education in the field doesn't make them an expert in the field. Right? You find the problem?
Think so?
You think so? Alright, what do you think it is?
You can't cancel out a minus b minus 1.
I can't cancel this out on both sides?
Yeah.
Why?
Because it's multiplied by a and on the other side it's multiplied by b.
Okay, but what does that have to do with anything? If I have 3a is equal to 3b, I can cancel out the 3 on both sides. Say a is equal to b. What was your idea?
I know it has to do with line 2.
With line 2?
I think so.
Has nothing to do with line 2. There's your next hint.
How about
It's
line
line 3.
Let's walk you through the algebra of line 3. A minus b times a is a squared minus ab. A times b, that's right there. A times 1, that's right there. Negative b times b, that's right there. Negative b times 1, that's right there.
There's got to be line 4.
What do you hate about line 4?
Yeah, line 4 makes the most sense.
From here to here, I just subtract a from both sides.
No, I'm joking.
So what's wrong with that?
Well,
line 5.
Oh, so it's line 5. From here to here, I just factor an a out of those. Notice if you redistribute it in, a times a is a squared. A times negative b is negative ab. A times negative 1 is negative a.
Well, I guess I meant it's going from line 5 to 6 that you made the error.
From here to here, where we cancel out 3 on both sides,
No, when you divide by something that could be 0.
could it be 0?
Yeah. If
How
a
do you
was
know?
0 and b was negative 1. So satisfies the top, and
Okay, so let's say that A isn't 0. I guarantee you that A is greater than 0. Then are we okay? So this is true as long as my A is greater than 0, then 1's equal to 0.
no.
No.
You can find other numbers. A is 5, B is
If-
4.
Then what?
Then you're still dividing by 0.
Then I'm still dividing by 0? How do you know I'm dividing by 0?
Because 5 minus 4 minus 1 is 0.
Okay, so what if we made A bigger than 10,000?
Oh my goodness. Okay. Then A is 10,002 and B is 10,001.
I wish you'd just notice it. A minus B minus 1 is always 0. What is A? It's B plus 1.
Oh, duh.
Minus B
Yeah.
minus 1. It's always 0.
You always find numbers, maybe.
Did I say line 4? I meant line 5.
Yeah, you work your way down. So that you did it one line at a time. You'll almost take as long as possible.
Almost.
So yeah, that is 0. That is 0. I said, look, these two things are equal, and when you multiply them by 0, they're equal.
Yeah.
In short, what do? I said, notice that 0 times 0 is equal to 1 times 0. So divide both sides by 0, and what do you get? 0 is equal to 1.
Oh.
Look at that magic.
It's too mean.
It's too mean?
Yeah. It's cruel.
What's
Not
cruel?
healthy.
Messing with his head, destroying the entire fabric.
I gave you, as we came into this with me telling you it was a bad proof.
What about that one proof you did where 1 equals -1?
So that one had to do with a concept that we were talking about over there, with the difference between a principal square root and a square root. I don't remember exactly what I did.
I remember what you did.
You do?
Yeah.
So I said something like, did I start with 1 or negative 1? Negative 1 is equal to, I probably said something like negative 1 to the 1
That's right.
is equal to negative 1 to the 2 over 2,
Yeah. And then you distribute the parentheses. To
which is
-1
equal
squared.
to the square root
No.
of negative 1 squared. Oh, did I not do it like that?
Well,
Oh, I
that's what
see.
you get to, you just skip the step.
So I said it's equal to negative 1 squared to the 1/2, which is equal to the square root of negative 1 squared, which is equal to the square root of 1, which is equal to 1. So negative 1 equals 1. Okay, so what's the problem with this one? Where do we cheat? In the middle. This one looks pretty solid. This one maybe. That one also a little fishy. Where do we cheat?
There again?
You're saying here to here?
No. The next one? Like,
Here to here?
one, yeah.
No, that's not the cheat.
Can't it also be negative 1?
No.
You're taking principal square root?
Yeah, that's what that means.
Oh. Okay. Never mind.
So where's my cheat? My cheat is right here. Going from this to this. I replace a 1/2 with the principal square root. This one was saying, what's all the square roots of 1? Which is 1 and negative 1. This is saying, what's the principal square root of 1? And so we just dropped off one of our solutions, negative 1. And so we lost a solution.
That's cool.
So we cheated.
I was wondering about that for a while.
We went over the problem with it.
You said, don't believe what everyone tells you just because it's a convincing argument, and then you left it at that.
Did I really?
Yeah. So I've been trying to figure that out for like the past 4 months.
Ah, that's funny. Well, yeah. Yeah, you can come up with a bunch, using that, you can come up with a bunch of problems. Anyways, yeah. So we'll end it there. That's the end of our chapter 1. We'll finally be starting chapter 2 now, for those of you who have a book and are doing homework and trying to get credit. Where's your book?